Okay, recording started. Good morning again. I hope that you could find everything in terms of video recordings related to the previous lectures. We already completed 2 weeks, so you should find 4 lectures in both YouTube and Virtual. If you see something missing, because you know I have to upload the videos in 2 channels, so sometimes it may happen that I forget something. I am checking, but if you see something missing, please let me know. Okay, so do you have any questions before I start? I know that I still have to discuss with you, but I'm planning to do it next week, the exam dates. So next week, I think I'll be able, maybe also on Thursday, but for sure by next week, we will be able to book the dates for the exams during the summer. And I apologize, but I was told that I cannot actually schedule any exam before the formal closure of the lectures. So it's, as you know, it's June 9. Unfortunately, it may be a problem. I don't want to expose you to possible problems later on for the registration of your career, you know. So I prefer really not to take any risk, given also that there are Erasmus students, just in your respect. Formally, I was told that the system doesn't disallow me to record any record exams before June 9, but formally, I'm not allowed to. So it's from an operational point of view, I could do that, but formally this is not allowed. So as I said, I don't want to expose you to some risks because the date of the exam is officially recorded. So, I mean, it's better that we stick on formal correctness. But in any case, at the latest next week, we will be able to book the dates. Okay, any question?
So next week we can book the exam?
Book the dates for June.
Okay.
For June, okay. So next week we will be able to agree on the dates in June. Okay, perfect. Any other question? Okay, good. So let me start at the Blackboard a little bit because I want to make a summary of where we are. Just 1 second. Okay, so what are we doing now? We are discussing probability, as you may remember. Why are we discussing probability? Because we are trying to estimate the risk which is generated by a given hazard, which can be expressed, as you know, as the product of probability times vulnerability times exposure. So we discussed a little bit about vulnerability and exposure, but just a little bit. We will get back to the discussion of vulnerability and exposure probably already today. But then we started the discussion on probability, and as I said, we are now experiencing an informal introduction to it. So where are we now? We defined the axioms of probability, and the axioms allow us actually to define probability, to define what probability is. So don't forget to learn this definition, because this may be the subject of questions, of course, both at the quiz and the oral examination. Like the classical question is, how would you define probability? Okay, and this is the probability of, as I said, a given event, which may be an earthquake, maybe a flood, maybe a drought, maybe other events like hurricanes, etc. Okay, and in defining the probability, we said that we may take different approaches to estimation. And we talked about the frequentist estimation of probability and the Bayesian estimation of probability. It's important to emphasize once again what I said at the closure of last lecture. Whatever is the estimation that we adopt, it must comply with the axioms, which are very simple. The axioms, as you may remember, it's let me just have a look, because they can be enunciated in different forms. So let's risk-based adaptation design here. Just 1 second. Just 1 second, I just want to see. Okay, good. So axioms of probability are here. Okay, the probability is greater or equal than 0. The probability of at least one outcome, at least one among the possible outcomes is 1. And the last axiom is the addition rule or additive rule, which means that if two events are mutually exclusive, the probability of getting as an outcome either one of the two is given by the sum of the two probabilities. Okay, so these are the three axioms which, as I said, whatever is the estimation rule that you adopt, you have to comply with these axioms. This is automatically satisfied when you adopt the frequentist definition, and it's not automatically satisfied when you adopt the Bayesian definition, which is based on your perception. So you cannot say that the probability of getting an head is 0.6 and the probability of getting a tail is 0.6, because the sum is 1.2, which is greater than 1. Okay? So we got here, and we also made some examples, very simple examples, which are tossing a coin and rolling a dice. These examples are very nice, very useful, because the outcomes are indeed mutually exclusive. So if you get an head, you don't get a tail. If you get, by rolling a dice, a 2, you don't get a 6. Pay attention to this feature of mutual dependence, because sometimes when you talk about risks, they are not mutually independent, the events. For instance, you may think of the probability of getting a flood during an earthquake. No, it's not a good example. Of a probability of getting a drought in the presence of climate change. Okay, these two events are not mutually exclusive. So climate change may imply more droughts. So you cannot say I get the probability of getting the two together by simply adding one and the other. Okay, they are not mutually exclusive. So pay attention to this fact of the mutual dependence, because actually this is what we are interested in. Sometimes we are interested in the probability of getting, say, a flood during winter after climate change, in the presence of climate change. So the two events, flood during winter, climate change, are maybe possibly dependent. When I made the example, earthquake and floods, one may say that they are not really dependent. So we can assume that they are mutually exclusive if we consider them occurring at the same time. So the moral of the story is just pay attention when you consider the possible outcomes from an experiment, whatever you define it. Look at the definition of your experiment, at the definition, at the features of the event that you are considering, and think at the dependence between possible outcomes. This is really important. Okay, we will see some examples. When we talked about probabilities, we also introduced the concept of random variables, and the case of the dice is a good example of association between the outcome from an experiment and a number. And the number is integer. This is another thing I want to underline. So far we talked about integer random variables. Okay, the outcome from rolling a dice is 1, 2, 3, 4, 5, 6. It's an integer. And we said that the probability of getting a given result, we can call it also probability mass. So if we say that the probability of 1 after rolling a dice is equal to 1/6, we said we can call it probability or probability mass. Just keep it in mind, because also terminology is important. If you talk with somebody and you hear somebody talking about probability mass and you maybe that you don't understand. So this is why I want also to give you an overview of the terminology of the terms that you may hear when you talk with people, with your clients, when you talk with your consultants. This is extremely important. So when I insist on terminology, you may think that this is not really relevant, but I really think that when you come to your profession, when you come to your life after your studies, it is extremely important that you understand people, that and you get understood by them. And this is why I think that also terms may be important. So just keep in mind that when you talk about an integer random variable, when you talk about an experiment that you can translate into an integer numerical result, you may talk of probability of getting a 1 from rolling a dice, or you may talk of probability of getting a flood, or probability mass of getting a flood. Okay? Good. And then we introduced the cumulative probability. We said that the probability of getting a result that is, let's call it I less or equal than 4 by rolling a dice, we said this is given by, for the additive rule, probability of 1 plus probability of 2 plus probability of 3 plus probability of 4, which is equal to 4 divided by 6, 2/3. And we called this one cumulative probability. Why this is important? It's important because, you know, if I refer, for instance, to floods, water levels, I know the level of the levee. I am interested in getting the probability that the level of the levee is not exceeded, because it means that it's the probability that I'm not flooded. So I may be interested in getting this cumulative probability, which means probability that a random variable is lower or equal to a given number. Term cumulative probability. This cumulative probability is also called probability of not exceedance. Probability of not exceedance. It's another synonym. I'm not sure I included in my web pages the term probability of not exceedance. This is not a problem for you. You just have to keep in mind that what I ask at the exam and the quiz is what you find on the web pages. But during the lectures, I may give you some additional information. And the additional information is for your, as I said, for your CV, your background. Okay? So probability of not exceedance. Keep in mind that sometimes people prefer to talk about probability of exceedance. Why? Because instead of being interested in the probability that I don't get flooded, people may be interested in the probability of getting flooded. So if you remove the not, you don't change the concept. The concept is the same. You compute, for instance, the probability of not exceedance, and it's extremely easy once you computed it. In the case of the dice, probability of less than 4, less or equal than 4, is 2/3. It's very simple to compute the probability of exceedance by using the same concept. What would be the probability of exceedance then? It's the complementary to 1 of 2/3. It's 1/3. Just beware of the fact that when we talk about probability, we talk of extremely simple concepts. They are extremely simple. If you think of the axioms of probability, it's a very simple definition. if we talk about this estimation of probability of not exceedance, you see it's an addition. I mean, it's very simple. And the way to make it even simpler is to associate the meaning to something that can happen. One problem with probability is that often we study it by just referring to abstractions. And then it becomes a little bit complicated. I mean, probability of exceedance, probability of not exceedance, probability mass, and then we have something more to introduce. It's important that you keep the association with something happening. And sometimes I make the association with rolling a dice because it's more instructive. And sometimes I make associations to examples like earthquake, floods, etc. Good. So we know about probability, probability mass, and which are synonyms, probability of not exceedance, or cumulative probability, they are synonyms, and probability of not exceedance, we can associate it to the probability of exceedance. Perfect. Now, let's introduce a little bit of a complication, and then I think we can, which is not a conceptual complication, but it's something that is a little bit more difficult to understand. It is the concept which makes the understanding of probability a little bit tricky. I think this is the critical step, what I am introducing, in gaining a full comprehension of probability, where with full comprehension, I mean a comprehension that allows me to really play with probabilities. And this complication is, what if the random variable is a real random variable? The dice is an integer. The result is an integer random variable. What if the outcome from my experiment is a real variable, like earthquake intensity, or water level, or duration of a drought? These are examples where the outcome from the experiment is a real number. Okay? In principle, it's no complication. In principle, it's the same problem. I can express the probability of getting flooded by analyzing a water level, which is real, or by simply focusing on flood, no flood, which is a binary random variable, which is then an integer, can be assimilated to an integer. So there is, I mean, the problem is the same. The process, the phenomenon is the same, but the result is a real. Now, what is the distinguishing feature of a real number? The infinite number of digits. You know, by definition, a real number has digits, may have digits, and the number of digits is potentially infinite. Okay, so let's raise the question, how can I compute the probability of a real number, of an outcome that is expressed by a real number? Okay, let's draw on the blackboard the axis of a graph of a real number. Just let me find, here it is, the eraser. So here is a graphical representation of a random variable, which we can call with the symbol capital X. Okay, and let's take a given outcome, lowercase x. Okay, here, this is 0, for instance. Let me start from 0. I could also start from a negative number, but let's make a practical example. So like the practical example may be that capital X is water level at a given location along a river. And my question is, what is probability of capital X equal to X? Okay, I may think of looking at data. So I may have, if X is water level, I may have some recordings of water levels in the past, observed in the past. These recordings are outcomes from the experiment. What is the experiment? The experiment is observing a water level, for instance, every day. But let's remain in a general context, observing the water level without specifying the timing. And then I can get several observations. If I observe the water level again and again and again, I may get thousands, millions of observations. Okay, so what if I want to estimate the probability of the water level being equal to lowercase x? So I may say, okay, let me look at my numbers, at my observation, and count the number of times I may adopt the frequentist approach. The idea may be, let's move forward as with the dice. Let me count the number of times I observed the water level, which is equal to lowercase x. And what would be the result of this counting? If I count, let me call the number of times with n, the number of times capital X is equal to lowercase x, what would be the result? 0. 0, because, I mean, my real number, my assigned real number has infinite digits. It's impossible that I get an observation with precisely the same number of digits. So it doesn't work, this definition. You may say, okay, let me limit to a finite number of digits. Doesn't work anyway. It doesn't work anyway, first of all, because you have to provide a formal definition. So a real number, you must adopt the definition of a real number. But even if you count, you limit the number of digits to, say, 10, this probability will be very close to 0. So it doesn't work. It doesn't work estimating in this way. So we understand that if we want to use the frequentist approach, we have to think of something different. Something different. By the way, do you know the reply to this question? Do you know how we can move forward with this estimation of probability? Do you know what is the concept that I am introducing? Nobody dares to say yes or no. The concept that I am introducing, I anticipate the terminology, so you get oriented in your maybe background, is the concept of probability density. It is something different, something additional. Probability density. And by reading it to the term, by looking at the term probability density, probably you already understand what is the conclusion, what I mean. Because actually, what is the probability of getting capital X equal to lowercase x? In practical terms, in technical terms, I am interested in knowing if I have a good chance of getting something around here as a result. So if there are several outcomes from my experiment that are very close to lowercase x, there is in my mind, I realize that there must be a high probability. So if there is a density of outcomes which is really high around x, this is the information that I need to know. And therefore, it's a kind of understandable that I have to refer to the density. So in practical terms, it's clear what I need. I need to get an estimate of the likelihood of getting more results close to here. And therefore, it is quite spontaneous that we think about density. But this is something additional. It's probability density is not probability, it's not probability mass, it's not cumulative probability. And I have to define it. And how can I define it? Okay. I mean, from the point of view of an engineer, what the engineer does when he has to deal with infinity or infinitesimal terms, because you know, here we are talking of something that is close to zero. What the engineer does usually is to discretize the domain, to discretize the results, transforming the real into integers. Discretizing means transforming the real into an integer. Discretizing means approximating the infinitesimal increments with finite discretized increments. So what I may think of doing is, let me identify a range here around x, which is x minus delta x, and here is x plus delta x. So I fix an interval around my interested value, and a logic step forward is that I count the number of outcomes that are falling into this interval. And so in order to get back to the frequentist approach, this I can do this. I can do it, and if I count the number of times, let me formalize it, because this is, I hope I am using the same symbols as in the web pages. X, okay, x minus delta x less or equal than capital X, less or equal than x plus delta x. I think the symbols are the same. This will be a finite number, okay? This will be something, okay, let me say a number n star, okay?
Professor?
Yeah?
From home, we cannot see the end of the...
Blackboard.
Yeah, thank you.
Yeah, no problem. Just 1 second. This is strange because I can see it anyway. Now you mean that you cannot read there, or because I see it on the screen?
Yeah, right now it's okay. I don't know. It zoomed in into the center, but now it's okay. Thank you.
Very good. So this will be a number, and the higher the so-called density that I have introduced, the higher this number. Okay, but this is not a density. This is simply counting the number of outcomes that are within a given range, and this is a bit arbitrary, because if I increase the value of delta x, then I increase the number n star, and the opposite if I decrease the range, the length of the range, the length of the interval. If I decrease delta x, then n star will decrease. So this is arbitrary. And in order to get something that is not arbitrary, what I have to do is to divide this by 2 delta x. And this is precisely what is called probability density. So if you get an interval, you count the number of the results that are falling within the interval, and you divide by the length of the interval, you understand that the number of times is an indication of probability. If you divide by the length of the interval, is probability divided by a range. So it's a density. And precisely the density is defined for delta x tending to 0. So if you look at the formal definition of probability density, formal frequentist definition is a number of experiments falling into an interval divided by the length of the interval, and we take the limit for the length of the interval tending to 0. And this is a reply to this question. I'm not estimating the probability, I'm estimating the probability density. So, you may say at this stage that there are some open questions. First of all, a first very practical open question. If I want to know the probability of getting flooded, how can I use the probability density? Or if I want to know the probability of getting an earthquake of a given intensity, how can I use the probability density? Because the probability density is a number that is very small. So the probability of getting flooded cannot be so small. And also, you may say, floods are caused by, for instance, water levels that are exceeding a given value, which is the height of the levee, but it's not only caused a flood by the water level reaching the height of the levee. I am flooded also if the water level is higher, 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 and higher. So I cannot be interested just in getting the probability of the water level reaching the top of the levee, which is very small. I am also interested in the probability of a water level exceeding the height of the levee. So this is already providing a first answer to the open question. So I don't have to look at the probability density, but I have to look at the cumulative probability. So this is the first open question. And then there is a second open question. You may say, this probability is divided by the random variable. So it's not really a probability, it's a probability density. And the unit is also different. Because it's, again, probability, which is by definition, by our previous definition, is adimensional. It's a frequency. But here I divide by the random variable. So I introduce the unit of the random variable. So if I'm talking about water level, which is measured in meters, probability density is expressed in 1 divided by meters. Okay, now let's find the final reply to my question. What is the probability of getting the earthquake of a given intensity? What is the probability of being flooded? Let me delete here. So what is the probability, let's say, let's refer again to a flood, because it is very practical, easier to understand probably. What is the probability of not being flooded? I can express it in this way. It is expressed by the probability of capital X lower or equal than X star, where X star is the height. I hope that I am using the H at the right place, height of the levee. So if the water level, capital X, my random variable, is lower or equal than the height of the levee, I am not flooded, okay? So what is the probability of not getting flooded? You see an association with the cumulative probability that we computed with the dice rolling. And in fact, this is also called the cumulative probability. Let me write it here already. So for both integer and real random variables, you can call you can use the term cumulative probability. So here, what is then the result? Let's suppose that I know the probability density. Let me call it fx. Sorry. This is the probability density. Let's assume that I know it. I estimated it previously. So I know the probability density. Then we make an experiment with R together and we compute it. So the cumulative probability is given by the integral of the probability density. Integral between 0 and x star of fx in the x. Look, let's look at this real number. So let's suppose that I want to know the cumulative probability here of not exceeding this value, which is corresponding with my finger, okay, x. So it's clear that I have to compute for each lower outcome the probability density times the length of the range that I am considering. So I get for 0 probability density, but the density is not a probability. In order to get it, you remember, to get from the density to the probability, I have to multiply it by the range. And then I pass to the next infinitesimal range. Another probability density multiplied by the range, another probability density, another. What is this? It's precisely the integral of the probability density over the range. The x is my range. Now we have everything what we need in terms of probability. To estimate the risk, to estimate, to assess climate change, everything. Once that we get the concept of probability, cumulative probability, probability of not exceedance, probability density, and we realize that the probability or cumulative probability is the integral of the probability density, once that we get this concept, we have everything what we need, everything we need. So we can now compute probability, given observations. We can compute the probability density, and we can assess how climate change may impact these probabilities. Because climate change, this is what climate change does. Climate change works on the probability, affects the probabilities. So you get that if you want to understand what climate change means behind the words, you need to know what is probability, how to estimate it. And then, of course, the next question, the next technical, very technical question is how climate change affects probability. But this is another story. The important thing is that you understand now that if you want to quantify the effect of climate change, you have to pass from probability. And the way is to work on numbers. Let's try to make an example which is not yet presented on the web pages, maybe that I include it after I work it with you. And this example is on the fly. Now I'm opening an R window. I work with R because it's very simple. If you want to make it in Excel, you can do that, but it is more complicated. So let me open an R window and let me try to get some numbers and estimate probability density and cumulative probability. We did it with rolling the dice. You remember that. now let's extend to a real variable. Any question? I would be interested in understanding what is your major question mark at this stage. So if you could tell me, look, everything is fine, but still, I find it difficult to understand what, this would be very helpful for me in order to clarify your doubts. Yeah, a question.
I have one question. Define the spectrum. What's the value we're getting? Like probability density means the number of events occurring within a spectrum. And if we multiply that with the integral, then that would mean a number of events that we're getting as a result. So okay. I'm not sure what we're getting. Are we getting a probability or a number of events that are likely to happen?
Okay. So the question was, I try to repeat for the people that are attending remotely. The question is, if I decide a range, you said spectrum, but I understand that you wanted to say a range of the random variable. And I am counting the number of events that fall within the range in order to compute the density. And then I compute the integral of this density. It's not clear to me what I am getting. And if it is the number of events or if it is a density, a cumulative density, something like that. It's did I provide a good repetition of your question?
Yes.
Okay, so you should say, when we decide the range, we count the number of results within the range, but to define the density, we have to divide by the length of the range. This is the important step that you don't have to miss. So the density is not number of events into a range. It's number of events into a range divided by the range. And then if you compute the integral over the range, because if you see there is a dx here, which is the range, the integral is again a number of events, because you computed number of events divided by range multiplied by range with the integral. So it's consistent.
Yes, but my result is a number of events.
Yes, the result is a number of, yeah, you are correct. You are correct. I should, good question, because I realized that I forgot one important thing. Let me just rewrite what I deleted on the blackboard. I should divide by the total number of experiments. So it's a frequency that I have to estimate. Let me just rewrite what was on the blackboard first. I think I wrote something like x minus delta x less or equal than capital X less or equal of x plus delta x. Okay, good. Divided by 2 delta x. And then I'm not sure how I called it. I think I just computed it. I just called it nx, something like that. And then I said that this is a density, which is true, but it's a density of number of events. It's not a probability density. And then I said that I indicate with fx the probability density. I forgot one step. This probability density should be computed as n x divided by, let's call it n tot, which is the total number of outcomes, the total number of experiments. So I forgot this step. I defined the number of events and I said this is a density, but it's not yet a probability density. The probability density is a frequency. It is a density of frequency, and therefore I have to divide by the total number of experiments. You see that your questions are very helpful for me in order to clarify the explanation, and I hope you get the clarification. Are there any additional doubts on that? In any case, we would have got it during the exercise, but it's important that we try to understand if there are still some concerns. Okay, let me make the exercise, which is on the fly, so please follow me, okay, because it's not something that I pre-prepared, because if I teach with something that is pre-prepared, I go fast. In this case, I prefer an interaction with you, okay? Okay, let me get, I don't remember if I have R here, I think yes, let's see. If it's not here, I may. It looks like it's not here. Give me 1 second that I install it, with the hope that I can succeed, because sometimes it's I'm not allowed to. Let's see. Okay, it works. Just 1 second. Okay, let's change the font. Otherwise, it's too small. So let's use 20. Okay, good. I think also remotely you can see my R console now. So first, we need some data. Okay, we need numbers. And these numbers may be observations of earthquake intensity, drought duration, or whatever, or temperature data, for instance, global temperature data, something like that. Okay, let's take a series that is generated with R, like I did for rolling the dice. What I would like to get is a number, a series that is close to what could be a real observation. So let me just generate something like, we can call it data 1 equal to, let's generate in this way. And let's get 1 million of data. Okay, this is generated from a standard normal distribution. And if you don't know what I'm talking about, just wait for half an hour. And let's now just say that these are numbers which may derive from the observations of water level, for instance. And I may show you a plot, like this is 1 million data. So the plot is a bit complicated, but let's see, plot data 1, just to give you an idea of what kind of numbers we are talking about. And let's make the plot with a line plot, because otherwise with dots it becomes messy. It's 1 million data, so it takes some time. We could also maybe, because it probably it's we should let's get the plot, but this is not let's focus on just 1,000 data, because otherwise everything becomes really difficult to see. Okay, so let's change the number, and 1 second, and let me generate with 1,000. Okay, because otherwise it's too. Okay, now this is the plot. Oops, sorry, this is the plot. This is more understandable. You know, when we talk about probabilities, which means an inductive estimation. We look at the results, like tossing a coin. Of course, the higher the number of experiments, the higher the numbers, the higher what we call the sample size, which means the number of outcomes, and the better. The higher the number of outcomes, the better. Okay, but for teaching, it's better if we refer to something that is shorter because it's quicker. So this could be observation of water level or observation of earthquake intensity. Let's just, so the question is now, what is the probability? We may have different questions, like what is the probability of getting a value that is lower or equal to, say, 1? You see that there are some outcomes that are greater than 1, some that are lower. So if, let's say, 1 means that I get flooded, if the outcome is higher than 1, I get flooded, what is the probability? Okay, so we have to count the number of points that are greater than 1. This is a very simple question. Okay, and then another interesting question may be, why should I concentrate on only one number? Let me get a graph of the distribution of probability over the full range from -2 to 2, from the minimum to the maximum. I want to get a graph that displays what is the probability of these numbers from -2 to +2. So a distribution, okay, not only for a given number, because I want to get an overall picture. And then I may ask the same question for the probability density. What is the probability density of a given number? What is the distribution of the probability density? Okay. Now let's start from computing. The simpler question is the first one. What is the probability? And it's not the density, it's the probability of getting a number that is, say, lower or equal than 1. This is very simple. We know how to do it. And this is the cumulative probability. Okay, let's compute it. Okay. Solve. Just 1 second. I close this windows because otherwise. And then we may say, okay, let's see, length, data 1, and then we put a condition, data 1. I think it is less or equal than 1. Okay, and this is the length. Oops, sorry. For some reason, I zoomed out, which is not what I wanted to do. This is the length. And let's see what is the length. It's just 1 second. Yeah. I made a mistake again. I'm still forgetting. Yeah, just 1 second. I'm still forgetting the bracket. Now it's there. Okay. It's 835. This is not the probability. To get the probability, I have to divide by the length of data 1. 0.83. This is the cumulative probability of getting something that is lower than or equal to 1. Okay. Good. I think everything is clear so far. So this is the first very easy question. Now, let's pass to the density because I want to go straight to the estimation of the density. And estimation of the density, in order to do that, I need to fix a range. Okay, let me look at the graph. Let me look at the graph. The graph shows that the result, data 1, is varying from -2 to +2, more or less. And then there are some outliers. But I mean, I need to get a range, to define a range, a finite range over which to compute the probability density. And I need to define a finite range because if I want to make the estimation of the density over series of numbers, I need to define this range. I cannot say it's zero, the range. It's infinitesimal. I need to pass to a finite differences representation. So the range may be, let's say, 0.2, 0.2. Okay, so let's try to estimate, again, by referring to the value 1, the probability density, by adopting delta x equal 0.2. Okay, let's try to do it. So again, length data 1. Now I have to put a double condition. So it's data 1. It's just 1 second, greater or equal of 0.8 and data 1 lower or equal 1.2. Okay, and let's look at what I have written. I want to find the number of values from data 1 that are greater than 0.8 and lower than 1.2. Because I adopted as delta x (0.2). Now, the question here is whether I've written the condition correctly, because it's a double condition, and I'm not sure I remember well how R wants it. Let's try to push enter. Let's see. There is something wrong here, because it gives two warnings. This gives to me the opportunity to talk to you. First, I don't understand. I installed R in English, and now it's working in Italian. Anyway, I want to take this opportunity to talk to you about warnings and errors in R. You can get in R errors, which means that it gives to you that something is wrong, like it happened here. If you look above, there is error, because I forgot a parenthesis. This is an error. It means that it doesn't give to you the result. It tells you the type of error that you made. Sometimes it's very easy, like in this case of the parentheses, to understand the error, what is the error. Other times it's not so easy. And then if you don't really understand, what I suggest to you is to take the error message and put it on Google. Better if you do it in English, and then you get indications on the error if you don't understand it. And then there are the warnings. The warnings means that R gives to you the result, but tells you that there is something that is not very clear to him. And in particular here, it gives a result which is not reliable. You see, it's 1000. It gives the full length of the data. And then the warning is, in data 1, in this instruction, there is a problem. And in particular, length is greater. I don't really understand what the warning is about, but in my opinion, is due to the fact that here the condition is specified in a way which is not correct. So let me just, when you get in a similar situation where you don't understand a warning, you don't understand where is the problem, you may have several solutions possible. One first solution is to make some trials. You go with trial and error, and you see if you can get to a result that is reasonable and without warnings. Another possible solution is to look on Google and to dial the warning in Google. In this case, I think it is not easy to get the solution through Google, because it's not very clear what the warning is about. And another possible solution here is to split the computation, the two conditions, into two computations with one condition. This would be probably the easiest way now to get out of it, but let me make a trial and error first, okay? So let me see, if I put only one, okay, perfect. The problem was just that I needed to put only a end, not two ends. You see that the warning disappeared, and the result now is reasonable. Okay, but this is the number of outcomes. Now, if I want to compute the probability density, I need to divide by the number of, by the length of the range. So let me clear the screen, because otherwise it's difficult to read, especially for those that are at home. Let me repeat the last instruction. This is the number of outcomes. Now I have to divide by 0.4. This is an estimate of the probability density. Sorry, and also not only by 0.4, but I have to divide by 1000. This is an estimate of the probability density. And here, there is a unit, again. It's the inverse of the unit of the random variable. Now, it would be nice to get a distribution, as I said, so not only for one, it would be nice to get a distribution over the whole range of the random variable. But before I do that, let me just try to estimate the density for other values, like 0, for instance. If I want to estimate the probability density of 0, let me just do it. So I have to put here minus 0.2 and here 0.2. I think, yeah, I am expecting a higher density around 0. Let's see. Yes, it's higher. Why am I expecting a higher density? It's clear. If you look at the graph, you see that most of the values are close to 0. Just visually here, there are less values. If you go to 1, there are less of them. Instead, there are several values that are close to 0. You may not be convinced by what I just said. And then in order to convince you, because you may look at the graph and see and say, I don't really see that there is a higher density of values around 0. Okay, so in order to better convince you, what I could do is to compute the average of our data. Would you agree that around the average, there are more values? And you see that the average is 0. So this is why also I was expecting around 0 more data, because the average is representative of what? Is representative of the most likely outcome or not. If you have to make a prediction, like what is the temperature value that you are expecting tomorrow, when you don't have any information, what would you say? You would say average temperature for Bologna in March. This is your best prediction for tomorrow if you don't have any information. The average is always the best prediction if you don't have any information. Average. And it means that it's the most probable or not. If it is the prediction that looks more understandable to you, it's the more probable. Okay. Now, again, and we have almost finished. I want to get a distribution of the probability density. So let me just go on the blackboard and clarify what I want to get. You see that these computations are very simple. I'm just counting. I'm just looking at the outcomes and counting. It's very, I mean, there is an integral on the blackboard, but it's the only one, because before than that, now I'm just counting numbers. Okay, so let's try to obtain this graph. Random variable, okay, here, and here, probability density. So for 0, I saw that it's 0.4. 0.4. This is 0. For 1, I saw that it's 0.25. 0.25, and this is for 1. This is what I did so far. Why shouldn't we complete this graph? Because this gives to me a clear perception of what I can expect for the future. Okay. How can we compute the graph? Simply, how can visualize it? How we can visualize it? So simply, I can make the same computation that you see on the screen several times. It's very simple. I just have to make it for 0, 1, I already did. For -1, for -2, -3, -4, etc. It is very simple. How can we make a repetition with a computer, with a programming language, but also in Excel? How can we make the same computation several times with some small changes, but the concept of the computation is the same? And remember, this is the advantage of a computer. The advantage of a computer and the advantage of a programming language is when you have to repeat the same computation several times for just different numbers. In this case, I have to make the same computation several times for different values of x. This is the real advantage of a computer, and it's the real advantage of writing, knowing a programming language and writing your own code. This can be done in Excel easily also, but in R it's much easier. So how can we make this repetition? There is a fundamental instruction in computer programming. In computer programming, there are just 2, 3 fundamental instructions, which are shared by all the languages. And this one I'm talking about is the cycle. I mean, I have to make the same computation several times. The only thing I have to change is the value of x. So let's make a cycle. And cycle means that you tell the PC, let me just take some room on the blackboard. I write cycle here. You tell the PC that you have to perform the several computations several times for different values of x. So usually the instruction that we use is a for. So for instance, I equal 1 to 100, which means please make this computation that will follow here for several times and use an index to count the number of times that you are doing. The index is I, and I want this index varying from 1 to 100, which means the first computation is for I equal 1, the second is for I equal 2, etc. Okay? And let's, before starting, let's write, for instance, x equal minus 0.4. Let's start from minus 0.4 from our variable. And then you make here the computation of the density, with the same instruction density, with the same instruction that you see on the screen. And then you write x is equal to x plus I divided by 10, for instance. So you increase the value of x of 0.1, and then you go back here and you repeat. It's very simple. The only thing, anytime you have to memorize the result somewhere in a vector, and then you make the computation. Of course, if you make 100 computations, you start from minus 0.4. And every time you pass to increase of 1/10, it means that then you have, at the first round, x is minus 0.4. At the second round is minus 0.3, minus 0.2, etc. So you cover the whole range. let's write it here. Let me clear the screen. First of all, I have to define the vector of the results. So density, data 1. Let's let's start from minus 0.4 to 0.4 with step of 0.1. So I have 8 steps. So let me put 0 8 times, or let's say 10 times, which is more. So I defined a vector of 0 10 times. Just 1 second. I just wanted to show you what is here. It's a sequence of zeros because I want to create a vector which will contain my results. Okay, good. Now we can write x equal minus 0.4. It was minus 4, not minus 0.4, the range, correct? Let's see. Okay, it was minus 4, minus 3 actually, but we can start from minus 4. So it's then if I start from minus 4, I have to go to plus 4. It's 8 with step of 0.1. The vector of the results should be increased. So let me just do it this way. Just 1 second. Control. Density data 1. Let me put it 100. I need it a longer one. Okay. Now we can start from x equal minus 4. This is the first value for which I want to compute the density. I am expecting that is 0 because if you look at the graph, it doesn't reach minus 4. So probably the first densities will be 0, which is fine, no problem. Now let me write the cycle. Now, of course, you need to know how R wants a cycle to be written. Of course, I know it. Just look on what I write and keep it in memory. So for, let's say, I in 1, 100. And then I can press enter. See, R puts a plus, which means tell me what you want me to repeat 100 times. Okay, and I need to open, given that I have several instructions to write, I need to open a curly bracket, because if you have in a for cycle several instructions to be repeated, you need to put a curly bracket before the first one and close the curly bracket after the last one. So let me see why it doesn't get the curly bracket here. I need to find, yeah, I see why. Just 1 second, no. It's here, so, okay. I got the curly bracket. Getting the curly bracket on an Italian keyboard is always an interesting question. So it depends on your PC, okay? Some PC have the curly bracket clearly written on the keyboard like this one. Other PCs don't have any appearance of curly bracket on the keyboard. And then you have to find the combination of keys to get it out. Usually it's Alt-GR, so, and at the same time the number 7. But in this case, it didn't work for me because actually there is the curly bracket on the keyboard, which I could find. But if you don't see on your keyboard the curly bracket, try with Alt-GR, which is the key on the right of the space bar. And by keeping pressed Alt-GR, you press 7. And it may appear. Otherwise, there is another solution that you can find. You go on the web, you find a web page with a curly bracket, and you cut and paste it. Okay, this is something that I did sometimes. Okay, and now the number of instructions. You see that after the curly bracket, R is still waiting. Now let me recall. Let me recall the instruction for the computation of the probability density. How can I recall an instruction? By arrow up. And it's here. Here we are. but I have to put the value of x here. So it should be x minus 0.2, x plus 0.2.
I didn't understand the instruction x equal to minus 0.
No, the instruction, sorry, this was a mistake. You see that I didn't type anything later on. I just did Control C to eliminate the instruction. So, you know, it was this instruction here, but I wanted to type this instruction here, x equal to minus 4, but I needed to first define a vector of the results of length 100. So I started typing the instruction, then I realized that I was missing the vector of the results. I just pressed Ctrl C, so I eliminated the instruction and I got the right one, density data 1. Is it clear?
So the correct one is density data 1, 0, 0, 0.
Yes.
X equal to minus 4.
Yes, you have to forget the blue x minus x equal to minus 0 point. This is something that was not executed. Okay, if you look at, now, later on we can look at the history of the instructions and you will see that that instruction is not recorded. Yeah.
So the red one is okay?
Yes.
Also, okay. So density data 1 equal to red.
Yeah.
Red is okay.
It's okay, and you have to forget what is before than that in the same line.
Okay,
I got a question for those who are attending remotely about the instruction, the fourth but one that you see on the screen, which is actually, it is the result of a cancellation of what you see in blue. If you look at the line last but 4 on the screen, there is a blue part and a red part. The blue part was cancelled, not executed. The red part was the correct instruction that was executed. Do you find yourself in my summary now? The last but 4 line, you have to forget the blue part and the red part is okay. Yeah, please, don't worry.
And what is the meaning of this function? Because I didn't understand it.
Okay, the meaning of the red one, which is the one that I executed. So the instruction is, the question was, what is the meaning of the instruction? Density data 1 equal to repetition, okay. The meaning is to create a vector to host the results. I am expecting 100 computations of density, and each time, each computation needs to be memorized, needs to be stored into a vector. And this vector has to be defined earlier into R.
Okay, so also the first function, repetition 010 is not necessary.
It was overwritten. It was overwritten because at the beginning I thought, by mistake, that I had to make only 10 computations. Then I realized that the computations were 100. And then I decided to overwrite the vector density data 1. Is it clear? And do you have any other question before we move forward? Yes, please.
The plus before the curly bracket is compulsory.
It's given by R. So it was not typed by me. It is just the fact that when R is waiting for some more, because the instruction is not complete, it puts a plus. Like he puts a plus, the meaning of the plus is tell me some more because I need more information. And you will see that when I will type now the return button, then it will present another plus, which is automatic. Okay, let me just see if everything is correct here. Length, okay, I think I am missing one thing here, which is the result. Here I am computing a density, okay? A density around the value of x. a value of x which was fixed at the start to -4, but then at any repetition is updated. But I need to memorize this result. I need to put it into the vector. So let me go to the beginning of the line here and write density data 1I equal to. So each time the result is placed in a different position in the vector.
Why we divided by 0.4?
Because it's the length of the range is 0.2 plus 0.2. Okay. I'm not sure it will be correct. We will see if it is correct. Because at the end of the story, probability has this nice feature that everything has to sum up to 1 for all the outcomes. Okay, if I type return now, and then I come to your question, you see that just typing return, it tells me something more, please. Okay, the something more is x equal to x plus 0.1, 0.1, yes. Which means that the next value of x is minus 3.9. Okay, and then if I type return, again it says, tell me something more, please. And the more is, there is no more, so what I just need to type is the closing curly bracket. And then it will go and compute. Now there is this little suspense, because if I made some mistake, of course it may give an error, something may happen. Let's see. Actually, the computation went correctly. Let's be getting the question before seeing the results.
That means that your range is now from -4 to 6, isn't it?
I think so, because let's see, if 100 means 10, yeah, -4 to 6.
Okay.
But it's not a problem. If you extend the range more, you get zeros out of the max value. It's not really a problem. Okay, and now let's check if everything is correct. First of all, here there is a question mark. The question mark is the extension of the range. So if the range is too small, you may get results that are not really stable, something that goes up and down. You get sometimes you get a 0. And if the range is too large, you get a representation that is too coarse. I just went by chance. I decided to take the range equal to 0.2. I think it is fine, but let's see what happens. So how can we, first of all, let's try to look at the results. 100 computations, this is the result. Okay, this can be, it looks reasonable. There are zeros at the beginning, zeros at the end. Let's try to make a plot to see how it behaves, okay? And what I am expecting by making a plot is a concentration around 0 of the probability density, and then something that goes down as I get far from 0. Okay, let's look at the plot. Plot density data 1 type equal line. Well, it's okay. I mean, this is what I was expecting. Sorry, let's make the plot XY plot. Let me remake it, okay? Because I want to put the random variable on the horizontal axis. So plot, let's say the, okay, let's look at this plot first, okay? This is the plot of the results, and these results are for x varying to -4 to 6, as you said, okay? It would be ideal to put on the horizontal axis the values of x, but let's for now look at just the results. You see that you have a concentration around 0 because you have the higher density in correspondence of 40, which is 0 because it's -4 at step of 0.1. You get 40 steps before getting to 0. And of course, now we could plot on the horizontal axis the value of x, but let's skip this for now because it's not really necessary. Now, the big question is the result reliable or not? This is the density, again. Is the result reliable or not? How can I check it? Remember, if I integrate the density according to this formulation, and I integrate the density from min to max, min x, max s, what you are expecting as a result here? 1. Perfect. Let's compute the integral. If the integral is 1, it's okay. This is the additive property. Additive rule, addition rule. So let's compute the integral now. Don't forget to the dx, the extension of the range, okay? Because if I just compute the integral by taking the sum, and the integral is a sum, remember this. Don't get concerned by the word integral, it's a sum, okay? So let me go in R. If I just, this is another example of a cancelled instruction, you see? This is another example of a cancelled instruction. This is not executed, okay? I cleared the screen, so if I just take the sum of density data 1, this is 10. Why? Because I forgot to multiply by x. And what is the density? What is the dx that I computed? Let's go back to this instruction for, I am repeating the for cycle. Okay. So what is the dx? Is in this case it's 0.1, and I will explain you after the break why it's 0.1. I leave you just reflecting on this, but just remember one thing, that I made here the computation with steps of 0.1. So here my dx is 0.1. Okay. So now if I make sum density, sorry, data 1 times 0.1, just 1 second, what's the problem here? Okay, I understand. I remade this computation here. I forgot to define x equal -4 at the beginning. So when I remade the computation, it went from x6 forward, which is 0 because there is nothing. So let's remake it. It's 1 minute and then we make the break. Let's remake this computation starting from x equal to -4. Okay. Okay, and then sum density data 1. Good. The only doubt that you may have now is why I took 0.1 as the x. The reason is that I went forward, you see in the fourth cycle, with steps that are 0.1. And therefore, this is my x, which I used in this case. Okay, now, next hour, no probability anymore. We pause it a little bit. But I just wanted to say that here we are done. Meaning that the other considerations on probability will be applied ones. But our, let's say, theoretical basis is closed here, okay? I just have a minor remark. You have to give me 5 minutes after the break to close this course on probability, because I realize now that it's better if I introduce also to you the concept of probability distribution, which is already introduced because it's this graph here. I just want to formalize it. Okay, good. Do you have any, or let's postpone the question later on, okay? Let's take a coffee. Okay, any question? You had a question. Would you mind asking the question to the audience, to the full audience?
Yeah, about
just 1 second, please. Thank you. Question.
I think it was when we divided this range of probability by 0.4.
Yeah.
And also tells us like why we divided by 0.4.
Yeah. Okay. So the question is, why did we divide by 0.4 somewhere in the computation? Let's see. Here, I think. Yeah. Why do we divide by 0.4 in the computation of the density? The reason is that you see the range is x minus 0.2, x plus 0.2. So 0.2 plus 0.2 is 0.4. So it's the length of the range.
Yeah, what does that give us? I understand that
Okay.
range, but in terms of is this a probability, and then we have to go divide it by 1,000.
Okay, because we divide by 1,000 because the number of dots falling into the range must be divided in order to get the frequency, must be divided by the total number of dots. And if I well understood your question, you mean you wonder if the estimation of the density is dependent on the range, on the extension of the range.
Can I use?
Yeah, please. You can come to the blackboard. Let just me share the screen. Yeah. Sorry. Okay, here we are. So you want to use the chalk? Can you please write here? We can delete because otherwise.
I can use this here. And what was the range now again? Between 0 and
Okay.
and then we have like and this is total. And if first the range was we computed all the dots here.
Yeah.
And then we divide that with small x by the total number.
Yes.
And that's 1,000.
Yeah.
But this, like what I understand, we took this and we also divided it by 0.4.
Yes.
So that would give us the frequency, just dividing small x with the capital X.
Yes. Small x divided by capital X gives the frequency. But then to compute the density, you have to divide by 0.4. Okay.
Yeah, maybe I.
I mean, there is the number of dots is divided by the total number of dots to get the frequency, which is an estimate of probability. But in order to identify, to estimate the probability density, we need also to divide by the range. And this is what we can see on the screen here, which is divided by 1,000 and 0.4. I hope it's clear. Are there other questions? Okay. Let me just show you as a closure. So into R, I have generated this series of data, which is data 1, which is 1,000 long. And I made all the cycle and the computation to compute the density. It would have been probably more, it would have been quicker to write plot density, because there is a function into R that automatically computes the density. Plot density data 1 and type equal line. There it is. And you see that the result is the same with respect to the graph that I had before. which is I can also overplot the other graph. Let me see, where is it? The plot, here it is. Let me just overwrite here lines. With the function lines, you add another series to the plot. And let's put it in red. Yeah, okay. The horizontal axis, it was different. Here in the plot that you see computed with the function density, you see that on the horizontal axis I have already the random variable. In the plot that I had before, you may remember that in the horizontal axis there was just the sequence of the data, not the random variable. So we cannot compare them. But let me just rewrite it here, the previous one, which still has the index on the horizontal axis and not the random variable. You see here this graph, and I think we could do this. Lines, density lines, density data 1. Right. Let's see if it works. Okay. Doesn't work, I'm sorry, but let's now go back here. So this is the one that we computed, and just look at the vertical axis so you can make a comparison. And this is the other one that I'm getting from R. And you see that it is comparable. What is the difference? The difference is just in the smoothing. This line is smoother than the previous one. Why? Because R automatically selects the range. So what I fixed to 0.2, R takes a different representation, a different range. And by changing the length of delta x, you change the appearance of the graph just in terms of smoothing. Okay. What I wanted just to say is that into R you have a function which is embedded to compute the probability density. But of course, if you apply the R function, you don't understand how it is computed. And in doing that by ourselves, hopefully we understood the concept, which is very simple. Okay, now I would stop here for now with probability. I said just before the break that I wanted to make a short addition, and then after the coffee I realized that it's better if I give you some time to digest it. We will get back to risk estimation. It's not concluded. And what comes next, I think it's the nicest part of it, because we will refer to our specific focus, which is hazards, natural hazards, and climate change. But I would prefer that now we dedicate this hour to a more narrative discussion, and then on Thursday we can get back to risk. This means that I am jumping back and forth with the lectures, and I, in particular, if I go to our links, now we are here, but we already dealt with the climate change problem. I have to change, as I said, the order. Now let me jump to the next one, sustainable management of water resources, and then we get back to risk on Thursday. And then later on, we will conclude our reasoning in terms of water resources. Now, why there is a focus on water resources now? The reason is that there are several ways climate change affects our communities, the human community. And therefore, adaptation to climate change may refer to several kind of impacts. So there is an influence of climate change on temperature, which means that we have to adapt to an increasing temperature with air conditioning, for instance, or by protecting the glaciers during summer with some kind of coverage. You may have heard that in the Alps, where they are more interested in preserving the snow for commercial use during the summer, they tried to devise the ways of cover the pistes in the skiing resorts with some kind of coverage, okay? Plastic, for instance, coverage with the white plastic in order to reflect the sun rays. So if the impact is related to temperature, we have some kind of adaptation. And then we may have the need to adapt to wildfires, forest fires, increasing frequency. And there are other impacts, of course. So there is an extended set of impacts. Very important impacts are related to water resources or to water in general, which means because water, as you know, is a fundamental agent of the climate system. And therefore, several impacts are related to floods and droughts. In fact, there are frequent mentions that are made by the scientific community and by the media to this kind of impact, which is concerning, in particular, when we talk about droughts, which are very extended usually. Floods are more localized, droughts are very extended, particularly when we talk about droughts, there is an increasing attention, an increasing concern, because also if you look at the recent occurrence of very severe droughts all over the world, this is a global problem. This clearly raised the problem of droughts, which is mainly related to water resources. So this is why we are making a particular focus here, not exclusive focus, but a particular focus on water resources. Not only because I am a water scientist, but because indeed it is recognized the problem of water resources as a concern that is relevant. And there is also another reason why we are focusing on water resources, because water resources are more difficult to predict with respect to other variables, other weather variables like temperature. And for a very simple reason, because of variability, temperature is more stable. Let me use this term, which is not really formal, but gives the idea. Temperature is slowly varying usually, while water resources, the variable that quantify the status of water resources are much more variable. If you think at rainfall, for instance, and therefore increased variability means that it's more difficult to predict. The result is that our models, our prediction models for the variables that are related to water resources are more uncertain. And this is why we are also more concerned. And this is why the scientific community now is particularly focusing on integrating the hydrological component into climate models. And in order to understand the problem, we need to understand the status of water resources, what are the current problems of water resources. And this is why I decided to include a lecture that is basically a narrative lecture on getting some orders of magnitude, getting some knowledge on the contours of the problem. So let me click on it and let me see. I don't remember if there is a PowerPoint. Just 1 second. Yes, there is a PowerPoint. Okay. The link is broken. This is interesting. So let me see. Where is it? I don't understand why. It should be. Okay. Let me just copy this link and let me try to find the correct one. And then I will check. Let me see. Oh, sorry, I made another mistake. Okay, it looks like I found a good one. Let's see. Let me check. No, it's not yet correct. Okay, so I'm going by trial and error, so don't. Okay, let me check. Give me 1 minute. It's called sustainability, okay. So sustainability, that's one second. Okay. I go to the previous version of my website and then I find it. Just give me 1 minute. I hope I find it. Okay, good. Okay, good. Here we are. One second. Okay. Okay. Now I want to close some window, just 1 more second, and here we are. Okay, good. Okay. Good. Okay, let's start with this graph here, which is also in the PowerPoint. So what is this picture? This is giving an overview of the quantitative status of water resources, and this is a static overview. This is a very classical picture. It is made available by the United States Geological Survey. What do I mean when I say static? This is highlighting the quantitative state of water resources just in terms of static volumes. It doesn't give any idea, any representation of flows. I will explain better. So if we consider the whole volume of water, which is on the Earth, we can look at the details of this picture in these terms. So on the left column, you see the total global water. And this means, this tells us that 97% of it, more or less, is salt water. And the remaining part, 3%, is fresh water. Okay, and actually, there is, if you look at the column, it makes a difference between ocean water and other saline waters, which we can aggregate in a percentage of about 97%. This is why I say that fresh water is 3%. Keep in mind that fresh water is the only water that we can use. So this is the first important information, meaning that had we the possibility of using of desalining in a convenient way the salt water problems would be completely solved. And keep in mind that 3% is enough to provide water for humans, even if with a demographic expansion to a triple human population with respect to now. So we have enough fresh water for everybody. The problem is its distribution. So, but in terms of volume, if we had the possibility to move water in time and space, both of them, because in some countries we have a lot of water during the winter and no water during summer, like for instance Italy. And therefore we need to shift water into time if we want to make sure that we have enough water at any time. And we also have the problem of uneven spatial distribution. Water is not easy to move in space because, but had we the possibility to shift water in space and time, the 3% would be enough for even, as I said, with an expansion of human population. It's not a problem in terms of volume. So you understand that volume is not enough in order to say if we have enough water for everybody. Had we the possibility to desalinate ocean water, you understand, if we have enough with 3%, it means that even if we desalinate only an additional 3%, it would be, I mean, given also the extension in space of oceans, the problem would be solved. Also in terms of spatial and temporal distribution, because we could desalinate when we need it, in time, and where we need it, in space. The problem is that currently desalination is requiring a lot of energy and poses also other environmental problems like the displacement of the salt, which is not easy. You cannot just rethrow the salt into the sea. This is not possible because if you concentrate the salt in a limited area, and also keep in mind that the salt is also polluted because when you desalinate water from the ocean, in the remainings from desalination, you get also the pollutants. But in any case, even if we decide, even if we had clean salt, we cannot release the salt in a concentrated way. We should be able to distribute it over the ocean, which is, I mean, you understand it's a problem. So in terms of energy, in terms of displacement of the residuals, desalination is still a problem. There are progresses because we are now trying to work on desalination through membranes. Currently, desalination is mostly carried out through evaporation, requires a lot of energy. But had we the possibility to make more efficient the desalination with membranes, the problem would be partially solved. We would require less energy. But still, desalination is considered an emergency solution, not a everyday solution. Okay. In any case, let's focus on the 3%, which would be enough. And if you go in the middle column, you see that glaciers and the ice caps. The middle column, what is the middle column? It's a zoom on the 3%, on the fresh water. So about 2/3 of this 3% is fresh water that we cannot use because it's trapped into glaciers and ice caps. So what remains for the human use is the 1/3 of the 3%, so about 1%, but still it's enough. And if you look at this 1% in the middle column is split into surface water and groundwater. And you see that in terms of volume, groundwater is the great majority of it is 30 times more. But here we should introduce the reasoning on flows. Groundwater is flowing with a very small velocity. Surface water is flowing with a higher velocity. So it means that even if it is a small volume, but it's flowing with high speed, it means that in terms of available resource is potentially delivering much more volume with respect to instead of a water body that is flowing with a very reduced velocity. I mean, it is if you take a picture, surface water, a picture is fixing time, is limited volume. But if you take a video of what is the volume flowing at each time step, you get a cumulative volume that is much higher with respect to groundwater. So this is why it's important to take into account not only the volume of a water resource, but also its flow, because flow means volume that if you integrate in time may become very significant. And also a higher flow means that the resource is more rapidly renewable. Because, of course, if groundwater is flowing very, very slowly, so if we exhaust it in order to get restored, it takes a long time. Surface water has the advantage that it's rapidly restored. And also if it's contaminated, restoration is much quicker. So this is why you shouldn't look only when you talk about water resources, not only at the volumes, but also at the flow, which is important. Okay, now let's take the 1% of the surface water and let's zoom over it with the right column. And you see that it's, if you look at surface water, there is still some of it that gets trapped, at least for some time into ground ice and permafrost, which is not the same thing as glaciers, because this is surface water that may be trapped temporarily. And then there are lakes, and then at the end of the story, there is soil moisture, marshes, rivers, living things, and atmosphere. At the end of the story, if we consider flow, what are the most important sources of water? We may mention rivers, even if they are half of 1%, so 0.5% in terms of volume. Rivers are providing most, let's say, a significant part, it depends on the country, of the water resources that we use. And then we have lakes, which in a way you can consider has part of the rivers, and there is groundwater. So this is why when we talk about water resources, we usually say groundwater resources and surface water resources. And when we say surface water resources, we mean rivers and lakes. These are the important sources. You understand that their displacement, it's uneven in space. So there are countries with a lot of groundwater. There are countries with a lot of surface water. And also in time, there is an uneven displacement. Keep in mind that precisely for the very reason that they flow at different velocities, surface water responds to climates quickly. Groundwater responds slowly. So it means that if you have a climate change, if you have a change in rainfall, you see the effect on surface water immediately. On groundwater, you may see the effect after 30 years. And it is really tricky because groundwater is difficult to observe, difficult to study. It's much more complicated than surface water. And the real situation is that, as I said, is sometimes the reaction time may be very long. Some people say even thousands of years. It means that if we have a perturbation now in terms of groundwater, we may see the result in 2200, so in 200 years from now. And given that the changes are so small, they are very difficult to detect. So if you look at a graph, you may say, okay, groundwater didn't change in the past 30 years, which is the reality for many regions of the world. Or you may say, yeah, after climate change, there is small changes in groundwater, but the problem is that the changes may be seen by our grandson, or maybe even later on. So, I mean, it is an issue, and surface water has the advantage that we see the results soon. And the same when you get a drought. You have a drought, okay, no precipitation, and the surface water gets exhausted soon, after a couple of weeks. It depends on the river, of course. Big rivers may get exhausted later, but if I had to give an order of magnitude, I would say surface water reacts by a couple of weeks. In some cases, even less than that, in some cases, a bit more. If you look at groundwater, the very surface groundwater, so the groundwater that is close to the ground, reacts, I would say, after a couple of months to a drought. But the very deep groundwater may react after 5 years, 10 years, 30 years. So the result of a drought may be seen in terms of groundwater resources after a long time. The problem is that groundwater resources are important, and for several regions in the world. And then, you know, this mystery around groundwater is the very reason why people say that it's better to be very conservative when talking about groundwater, when using groundwater. Very conservative means that whenever it's possible, we should stick on surface water. And and try to save groundwater. And this is why also, in the presence of climate change, several institutions and several researchers say better to increase our potential to use surface water rather than the opposite, because it's a natural reaction to a drought. You get a drought, and then you get surface water exhausted after a couple of weeks, and then the natural reaction is to use the groundwater. But actually, there is the feeling that this is not very prudent, not very conservative. So this is why, even if when you look at the graphs of groundwater, the data related to groundwater, you don't see big changes. So you may think that, okay, it's not a big problem. This is why still several institutions and several researchers say better to increase our capacity in terms of surface water. This is, when designing adaptation, it's clear what it means. If you want to rely more, if you want to adapt to drought by using more groundwater, you dig more wells, okay? Or you increase your pumping capacity, groundwater needs to be pumped. If you want to adapt by increasing our capability to use surface water, you have to build dams. Dams, the purpose of dams is to shift water availability in time. Okay, you store water during the winter here in our regions, in our continental climate, in order to get some water volume available in summer. It means a time shift. This is the purpose of a reservoir, to shift in time water resources availability, okay? And of course, dams have an environmental impact. There still remains the problem of the uneven spatial distribution, but we will talk about it later, okay? It is a different kind of problem. It requires different solutions. So adapting to the uneven distribution of water in space requires a different adaptation action with respect to adapting to water resources uneven distribution in time. Dams are a relatively easy solution. The problem is that they are causing an environmental impact that is very significant. They have several advantages. They allow also the production of clean energy, and it's more than clean. It's also renewable, because it's hydropower is renewable and can also be repumped back. So it is, I would say, twice renewable, not only because through the water cycle you get water back over the mountains. I mean, after producing hydropower, you release water downstream, and with the water cycle, you bring back the water to the mountains. This is one way of making water resources renewable. But there is another way of making them renewable, which is by pumping back. So you release water downstream, and you pump back into the dam upstream. And this is another way of making water resources and hydropower renewable. So you may say, what is the purpose of pumping back? Because I need energy. So what is the purpose of spending energy to produce energy? The purpose is very simple. Energy cannot be stored. Like water is difficult to be stored. So sometimes you have excess of energy, and sometimes you have lack of energy. For instance, if you think at the solar energy, it's available during the day, but not during the night. And the result is that during the day, I have an excess of energy which I cannot store. So the solution may be that you use the excess of energy during the day to pump back water into the dam. And then during the night, you don't have the solar energy, but you have the hydropower which is available. So this is, this is just to emphasize what are some kind of adaptation options, which on the other hand require, have an environmental impact, because the environmental impact of dams is really very significant. When we talk about these issues, we understand why there is great attention today on the so-called water, food, energy nexus. Water, food, and energy, they are strictly related. Maybe we have some time to talk of it. We will see. Anyway, this is a picture of water resources, which it's very popular. And I want to emphasize, I have some colleagues, international colleagues, who are criticizing it for the lack of representation of the flow. So it's interesting also to look at the flow. And in order to look at the flow, let me just look at the source of the flow. The source of the flow is rainfall. And this picture, which is providing a global distribution of rainfall in time, I think it is a nice way of looking at the uneven spatial and temporal distribution. You see that rainfall is concentrated. Rainfall is the blue color. Rainfall is concentrated in some regions of the world. And where you see white means really lack of rainfall, severe lack of rainfall. And also in time, you see that there is a significant shift in time of water resources availability in the different months. So this is our problem. I mean, we have enough fuel. Here, rainfall is the fuel of the water cycle, and it's also the fuel of water resources. But it's the spatial and temporal distribution that is a problem. Let me just look for a second at the web page, because I want to make sure that I'm not missing something, because if I look at the PowerPoint, no, I would say that it's okay. Perfect. So let's here. Okay, let's have a look at climate. This is a popular classification of climate that has been introduced recently. It's the Köppen climate classification. And it is providing a very quick overview of the distribution of climate over the Earth. You see with, again, with the blue, you see the abundance of rainfall, and in red, you see lack of rainfall. In green, you see, in green and light blue, a good situation. If you look at Europe, there is some yellow. Yellow means water scarcity already in the south, and you see a good percentage of green and light blue, which means that if you look at the northern hemisphere, the situation is quite okay, let's say, in terms of water resources availability. This is the reason why in the north of Europe there is not much concern about water resources, and therefore less concern on the impact, the direct impact of climate change. And this kind of classification is nothing that can be asked at the exam, but it is important that you get a perception of the distribution of rainfall and distribution of climate, because in order to understand what are the impacts of climate change, and therefore where we require adaptation, you need to understand the features of climate, first of all. I would say that it is important to emphasize already now the impact of climate change is much different in space, much variable in space, and there are different impacts of climate change that are concerning depending on the country. The solutions are always local solutions. When we talk about adaptation, we cannot have a global recipe. The global recipe may be to adapt and to minimize the impact of climate change, but the practical solutions are different. So even in the south and north of Italy, adaptation measures are different. Therefore, it is very important, and here the research is working, but without a satisfactory result so far, to find a way to couple the climatic behavior and climate change behaviors with the local conditions to get an indication of where is a risk more relevant, so where probability of getting an hazard increases actually, and where instead climate change is not a big concern. I think I already made to you an example which in my opinion is very significant. If climate change is affecting the extreme rainfall, which means like thunderstorms, rainfall with very short duration, just gain this idea. When you talk about the rainfall that makes you wet in 30 seconds, it's generally a rainfall that lasts for a short time, like the summer storm. The rainfall that lasts for 1 week is not intense rainfall, it's very light rainfall, but continuing for a long time. This is a specific feature of rainfall, which we know from our day-to-day experience, but that you have to keep in mind. Now, if the change is in the short rainfall, like summer thunderstorm, the impact is concentrated on small rivers, on creeks, not big rivers like Po River, Tevere, Arno, or Danube. These rivers, these huge rivers, are impacted by long rainfall. When do you get a flood in the Po River? After 1 week, after 10 days, after 2 weeks of rainfall. Maybe a rainfall that is very slow, very, light, but it's lasting for a long time. And then you get concerned about the big rivers. When do you get concerned about floods like the one that we had in the Marche region, the ones that we have frequently in the Liguria region? In summer or late summer with very intense thunderstorms. So, moral of the story, if climate change is changing short-term rainfall like it looks it's happening, then where is the impact concentrated? In small rivers, small creeks, small river basins. So we have to couple these two indications. If we want to estimate a probability of something occurring, of an hazard occurring, we have to mix the climatic, we have to study together the climatic features, and in particular climate change features, with the feature of the land. Okay, we start from climate, and let me just look at the next one. I think I can stop here for now, and on Thursday I will move forward with this lecture, and on Thursday or Monday I go back to risk. Questions? Thank you, grazie. If you have any question even later, you can send emails or you can write on the chat of Teams, okay? And so that everybody sees your question. I don't really mind. I would appreciate if you started some discussions also on Teams in the chat, because also I can interact with you. I prefer that solution with respect to individual emails. Good, grazie, thank you.